As we start into Chapter 7, we're going to hit an Algebra 2x topic dealing with polynomial functions. Section 1 actually has a lot of objectives. You're going to notice here that it covers 6 different learning objectives in just Section 1. A lot of it is just vocab. So first objective, define if an expression is a polynomial, identify the leading coefficient and state the degree. 2, find the zeros or x-intercepts, and then find the y-intercepts of a function algebraically. 3, determine if a function has an overall relative maximum or minimum. 4, state intervals where functions where it's increasing or decreasing and positive or negative. And 5, write a polynomial equation for volume of a rectangular prism. And then 6, determine dimensions of a rectangular prism, which is the volume when it's maximized. Now, these notes particularly cover on 1, 2, 3, and 4, and we do get into 5 and 6 when we do a project after the notes on 7.1. So let's dive into the notes. The definition of a polynomial function is this. It's an expression in this format right here, and it's important to look at this. The letter n, when you really look at it, is going to be this exponent. It's where n is a positive integer. So n cannot be a negative integer, and it must be an integer, so a whole number. The various types of integers that you can have for n would be anything from 0 all the way up to infinity. A nice example would be this. If a polynomial function might look like something of this nature, 3x squared plus x plus 1. That's a polynomial. If we didn't have the 3x squared there, but just the single x, like that, that would be considered a polynomial. The key is that the highest exponent it's raised to, again, has to be a positive integer, as do all the other exponents within the function itself. So let's talk about what would be the various names of these. The degree is the highest exponent. So in terms of the definition, it's the highest exponent once it's in standard format. Okay. Standard format is the highest exponent first, followed by the others. So if I had a function such as this, I had like 4x to the 5th, and then I might have negative 3x squared, followed by plus 6x minus 5. This would be considered in standard format. The leading coefficient is the coefficient of the first term once it's written in standard format. So for this case, the leading coefficient of this problem is number 4 for that. Now, in terms of names of what we call things, if a function has degree 0, this is what it may look like. It's degree 0 because it's actually times by, you just don't see it, this is multiplied by an x to the 0 power. Anything to the 0 power is 1. So if it's of degree 0, we call this a constant. Now, when we get a degree 1, here's a nice example of degree 1. 4 times x to the first power, that's the first degree. This is considered to be a linear polynomial because it forms a line. Number 2 is considered to be a degree 2 polynomial. This is not in standard form as it's written. The standard format of this particular quadratic is what we would call this, is going to be negative y squared plus y. The leading coefficient of this particular expression is negative 1. Now, if we have a third degree polynomial, that is going to be called our cubic. A fourth degree is a quartic. A fifth degree is a quintic. Which is the very same type of numbering word system as used in all of mathematics. Now, if you look at the quintic function, or the function, a polynomial of degree 5, it's another way of saying it, this is written in standard format, and the leading coefficient here is a 1/30th fraction. Now, this function here, what is the degree of this particular function? If you state that, you can tell it's going to be a polynomial of degree 5. Its leading coefficient is negative 1/10. Now, get rid of the word degree here. It's not the right thing. But these next 4 lines here are going to talk about how do we name a polynomial based on the number of terms in it, not just the degree or the highest exponent. In this case, if we had a monomial might look like something like this, 5t to the 4th power. That's one particular term as a monomial. If we add something to it like minus t cubed, that is now going to become a binomial. A binomial has 2 terms. The terms are the things being added or subtracted. Trinomial, let's add to it a plus 7t squared. That would be a trinomial, something with 3 terms. And then lastly, if more, careful on the spelling there, if there's more than 3 terms, we don't call it a trinomial. Specifically, what we do is we call it a polynomial of degree n. And you would fill in whatever degree it has. So for this trinomial up here, maybe I might add, minus 6 at the end. This has 4 unique terms, so what I would say is it's not a trinomial or anything of that nature. I would say it's a polynomial of degree 4. Now in this particular example that I have up here, do notice the leading coefficient is the number 5, and it already is in standard format. Now this box activity we're actually going to skip for now and revisit it after we take the notes and do the homework on section 7.1. Alright, let's look at this, the graph of polynomial functions. Now let p be the polynomial function with this particular equation. They want to know what degree this function is. Now folks, be careful, this is not degree 3 nor is it degree 2. What you technically would have to do, and we don't necessarily need to go there, is write this out longhand and do x minus 1 3 times, and then x plus 4 twice. And then you'd want to multiply this polynomial through and get it in standard format. So there'd be tons of distribution here. I'm going to tell you, when you do this distribution, what's going to end up happening is the first term is going to be x to the 5th, followed by some other terms. And we can just see that in this format that the highest power will be a 5, so it's going to be a degree 5 polynomial. Now, they also want us to find the y-intercept and the x-intercept of this graph. Now, what I would do is actually get your graphing calculator out and do a quick sketch of it. Type it in the calculator, and what you're going to end up finding is you're going to have an x-intercept at a positive 1, one at negative 4. We're going to see that the y-intercept is going to be all the way down at a negative 16. An incredibly rough sketch, because I actually don't even have my calculator with me, might look something like this. It's somewhat parabolic shape, but not quite exactly. Okay, now I want you to find this stuff algebraically. That was one of your objectives, and you're going to have to know how to do that. Prove it to me. So take a look at, let's start with the x-intercepts first actually. You're going to notice the x-intercepts happen here at the order pair 1, 0, and negative 4, 0. X-intercepts are unique in that they always happen when y is equal to 0. So they're easy to algebraically find. All you do is set y equal to 0. Now when you look at this function notation, you don't see a y. Well, this is just y here. P of x is equal to y. So what you can do is set the whole function equal to 0 and solve. Now the nice thing about this equation is that it's already factored for us, and you can use kind of that zero factor property. What you can do is take each factor and set it equal to 0 and solve. So this is the first factor, set it equal to 0. Now to solve for x, I have to get rid of the cubed and the minus 1. First get rid of the cubed by raising it to the reciprocal of 1/3, which is the cubed root. 0 to the 1/3 power is just 0. And then this is x minus 1, which you solve, and you're going to get x is equal to plus 1, which is the one y or x-intercept that we already determined. The other x-intercept, let's take our x plus 4, which is all squared. Set that equal to 0. To get rid of the squared, take the square root or raise it to the 1/2 power. That's going to leave us with x plus 4 equal to 0, or x equals negative 4, which is exactly what we had already identified. Okay. Now on the other side, they want us to find the y-intercept. Okay, now to find the y-intercept, that also has a unique feature. This one actually happens at 0, -16. And if you see the connection, here x is equal to 0. So to find the y-intercept, all you do is set x equal to 0. So if we do that, we're going to have p of 0, if we plug it in the function notation, is 0 minus 1 cubed, 0 plus 4 squared. This will be -1 cubed, which is -1. 4 squared is 16, or a -16. So this is mathematical proof that the y-intercept happens at a -16. You definitely want to know how to do the x-intercept and y-intercepts algebraically. Now this next slide is called the extrema of a functions. And what it is it's really calculus vocabulary. And I'm going to show you how you can make this easy to understand it. There's 4 vocab words. These 2 first vocab words you've heard of before. They're the extreme values. A function can have an extreme maximum or a minimum. The plural for an extreme would be the extrema, by the way. If there's more than one extreme, you'd say there's multiple extrema. And a function, again, can have a max or a min. And what you do is you look at the function here as a whole, the whole entire function, and you see if there's one maximum or one minimum. Then there's the relative extrema. You're going to see what type of high points and low points are within a particular function. And this is mainly within a particular interval of the function. So you can have a relative local maximum or a relative local minimum as a certain partition of a function. For example, this graph on the left, that particular portion I circled is a local maximum of the function. Whereas this graph right here, the entire function does not have a maximum. There's not one ultimate high point of this particular graph here. This goes on to positive infinity and down to negative infinity, which means it does not have a complete maximum, nor does it have a complete minimum. But it does have relative mins and relative maxes. Graph number 1 here, again, this right here is stated as the relative maximum, and this one right here is stated as the relative minimum. So if we were to do matching on this, we can tell that these vocab words go with the first graph. I'd like for you to pause this video and see if you can figure out where these other 3 graphs go with which of these other 3 groupings of definitions. So pause it and see if you get it right. Okay, if you got these arrows here, let's start off on the far left. Look at graph number 4 here. This particular graph has no maximum because it goes on to infinity and no minimum as a whole. It also does not have any unique turning points in the middle of it. It looks like there's some humps going on in here, but there's never really one particular high point or low point. So for graph number 4, this it is actually going to match up with, if we look at my arrow, this one right here, there is no minimum, no maximum, no relative minimum, and no relative maximum. Okay, graph number 3 is a little more simple. Graph number 3 goes to this last bit of words here. There is no minimum on this particular graph. It actually goes to negative infinity all the way down here and negative infinity down here. The graph does have a maximum height though. As a whole, it maxes out right here, so it does have a maximum. At the same time, it has a relative maximum because there's a certain section of the graph that actually maxes out. And that section, if you looked at it, would just be like that little boxed in section. Okay, and then the last one by default, this graph number 2 with all the humps has lots going on. If you take a look at this, what it says is this graph actually has a minimum at the point C, which this is the lowest part of the graph right there. There is no maximum because this graph goes on towards positive infinity on both ends of it. There are a variety of relative minimums. There's a minima at C here, at E, and at G. And there's also a maximum at F here and at D. So at D and at F, there's 2 little maximums if you were to kind of look at the graph in just small intervals or small kind of boxed off points. So hopefully you understand that definition. Now if we look at this example 1 here, we're back to the particular graph that we did before. So let me pop that on the screen real quick. Again, roughly we had something like this. And it says use the calculator, graph the function, and determine its relative minimum. Now its relative minimum in this case, I believe does happen at the, maybe somewhere in here. Now what you can do is go to the graphing calculator, and I can't show you on this screen, but go to second calc on the graphing calculator mode, and you are going to select minimum. And what you're going to do is a left bound, right bound. So go somewhere to the left. This is going to be your left bound, and maybe put the cursor there, and then go to your right. Somewhere over here would be your right bound. And then they're going to ask you to do a guess. Do that and you will be able to find the minimum point on this graph. This graph does have a minimum, and it also has a relative minimum at the same point. It does actually have a point where it bottoms out, and we can find that. Now, if that bottoms out at the y-intercept, then you can use your definition of y-intercept, which means set x equal to 0 and solve. But for our purposes right now in Chapter 7, to find minimums and maximums, I will let you use the calculator and do second calc min or second calc max in the calculator. So you can use the calculator for minimums and maximums only though. Now we've discussed maximums and minimums, relative maximum, relative minimums. We have 4 more vocab yet. The next one is where an interval is increasing or decreasing. And increasing and decreasing looks at the slope. So to fill this in, increasing if the slope of the line of a particular interval is positive, it's increasing. And it's considered decreasing if the slope of the line of a particular interval is negative. So what I want us to do is to actually take this graph right here, put it in the graphing calculator and do a quick sketch of that, and then figure out, determine where we would say it is increasing and decreasing. Now here's what this particular graph would look like. It says here a relative maximum occurs when x is about negative 1.3. So the relative max is right here, and the relative minimum occurs at about 1.3, which is right there. Describe the intervals where f is increasing. Now folks, all you need to do is just travel left to right like you read a book, like you read the graph, and just see when the slope is positive. As I travel, we can tell that the slope is positive from here to here. It's also positive from here to here. On the flip side, the slope is negative from here to here. Just if you're going uphill, it's positive. It's downhill, it's negative. Now do state this in interval notation. So I would say that the function is increasing for all the x's less than negative 1.3. And then it comes back and it's for all the x's greater than a positive 1.3. Now be careful, at this turn here, it's neither it's not positive or negative. It's actually is a turning point, and so what happens is if I were to draw a line, the slope right here at these 2 turning points is flat and the slope is 0. So you don't actually include the turning points. Now on part B, where is the function decreasing? It decreases everywhere here. Again, we would say it's going to be, in this case, it's in between negative 1.3 and positive 1.3. You can tell this section here is one complete line. It's not broken up like the 2 blue ones are, so it can be written as an in-between statement. All the x values that are in between fall in this line, and that's how you would write that. Now there's 2 other vocab words that are not formally introduced, but we do need to write that down. One would be a negative. When is a function negative, and when is a function positive? So let's just jot that down here. The function is negative versus positive. It's positive when it is, the y's are positive, so above the x-axis. And it's considered negative when it's below the x-axis. So we are going to want to understand how to find positive and negative and increasing and decreasing on a function. So let's look at this example. Consider the graph at the right. The x coordinates are all labeled with different letters. They want us to use the letter labels and state the interval where the function is negative. Now, again, definition of negative is where it falls below the x-axis. So the graph here falls below the x-axis there, here, and here. So how I would state that is this. I would say it's negative at the a's. So I would say it's all of the x's are less than a. Remember, less than points left. So all the x's less than a. It's also all the x's in between. It looks like c and e. So I'm going to say for all the x's in between c and in between e. And then all the x's greater than g is what we would call a negative. So this is where the function's negative. Now, they don't ask for this particular example, but folks, it's positive where it's above the x-axis. So there and here in those two components. Okay, let's continue on. Let me get rid of some of those that I just did. All right, the next part they want to know is where is the function decreasing. So we'll do decreasing in the blue. Remember, decreasing is when the slope is going downhill is where it decreases. So the decreasing for this function we're going to have right over here. This decreases at this point in time. The slope is going downhill. That's from the point F on, so that's for all the x's greater than F. It also is going to decrease here at point B all the way over to point D, it looks like. So B and D, it has decreasing. So I'm going to say everything greater than B, but everything less than D. Okay. Now, the other thing they did not ask us about is where is this function going to be increasing. Increasing, the slope's positive, so it increases here on this side, and it also increases right here if they had asked us where to find that. Okay, let's continue on again with the vocab. Remember, we have what goes together. We have positive and negative, increasing and decreasing. You're going to be able to want to find where all these things are on a graph. Here's another picture. They want to know where is the function positive. Remember, positive means it's above the x-axis. So it's positive from here to here. It's positive from here to here. And it's positive from there. So if you want, you can pause it and actually try how to answering these positives and increasings and see if you get it right. Okay, it's increasing is where the slope is going up. So it's increasing from here to here, from here to here, and from here to here. So pause the video and see if you can write the correct interval notation for that. Okay, and here is what you should have come up with interval notation. Notice all the interval notation does not have an equals to. For the function to be positive, it has to be above the x-axis. Between the point A and the point C here, it's on the x-axis. The x-axis there is 0. 0 is neither positive nor negative. Now again, in terms of the increasing, where the slope is, right here when I get to the point B, the slope at point B is flat. The slope, you do not include it as increasing in this function. This last slide here just wants you to realize a few things. The zeros of a function. Folks, the zeros of a function, when you have a linear function, you can find the zeros by setting y equal to 0. The zeros are the x-intercepts. So the x-intercepts are the zeros, and to find it, you set y equal to 0. Okay, that's your best rule of thumb. That's what you would do for a linear function. For a quadratic function, you could set this equal to 0 and you could solve. You could solve a quadratic function by using the quadratic formula. You could factor. You could complete the square. And you could graph. Now I'll tell you, in most cases, you're going to use the quadratic formula or you're going to factor to solve quadratics. The third type would be a cubic function. Again, set the function equal to 0 and solve. A lot of the times, if you remember your factoring, if you're good at that, you could factor this. Graphing is going to be an initial way to do it. Our ultimate goal, though, for Chapter 7 is to figure out how do you find the zeros of a function like this by using factoring and doing some type of graphing methods. And they want you to realize, too, you can find the zeros here where you notice on this particular function here where the sign changes. So where it goes, here the y's are positive, here the y's are negative. So what happens is you see a change happening in the y. That's what they're saying here. The y's are at one point positive, and then they go to negative. And that's where you actually see the 0 pop up. Your homework assignment here is what's listed. You can skip 3, 4, and 7 for the regular assignment. And for 14 parts B and C, I want you to find the y-intercept and the x-intercept. And you need to show some algebra to prove to me you can find it. You can use your calculators to confirm, but prove it with the algebra.